How do I go back to the normal mode in which I actually have the...
Okay. All right. Well, welcome everybody. Thank you for coming to our first broadcast seminar. Our first seminar was actually last week, and we're in a new room, so bear with us if we have any technical problems. It's a pleasure to have today Dr. Dror, who's, of course, just joined the department, the ECE department at NC State. Dr. Baron got his PhD from University of Illinois at Urbana-Champaign, and he actually has had a lot of experience both in industry as well in academia. He did a postdoc at Rice University and also at the Technion prior to joining us at NC State. So today he'll be talking about some of his research. He's got a broad set of themes of research, and today he's going to talk about source coding. And it's a pleasure to have you. Thank you.
The floor is yours. Okay. Can we get the computer? The laptop or? Laptop. So while we're getting the computer, I can start saying that this is work from the last year and a half or two, which is actually not entirely mature, as we will see toward the end of the talk. The theory is quite well established, but more practical aspects need to be discussed. Once we get a screen, I can move on to the next slide. Okay. So the problem here that we're really dealing with is that, of course, the world is, what is that thing about? Okay. So the world is, of course, moving from an analog processing type of style to a digital processing type of style. This is taking effect over a lot of different sensing modalities, and at the same time, there are some sensing modalities that are really dominating the amount of data that is out there. I read recently that video reportedly accounts for over 80% of web traffic this year. I don't know if that's true. I find it a bit hard to believe, but if somebody wrote it, then I'll take it. And that really means that any reduction of 5%, 10% in the number of bits required to encode this video at the same quality of video would really have a drastic impact, because as we know, this is, web traffic is a multi-billion-dollar industry. So we're highly motivated to reduce that, and we really have two types of data compression. One is the lossless type, where we have an input and we want to reproduce it perfectly at the output. And in order to reproduce it perfectly, and that could be important for, let's say, text files or executables. This is interesting. In order to reproduce it perfectly, we may need to have a lot of bits. Now, as I just mentioned, in the video case, we don't really have so many bits. It's very costly. And on the other hand, it doesn't really matter if it'll arrive perfectly, because the human visual system is capable of, or rather capable of not being overly sensitive to minor differences between the input and the output. And I'm sure that Joel would be able to elaborate on what I just said very significantly. All right, so we're allowing some distortion, but we want drastically lower data rates. Now let's formally kind of set up our problem. We have an input x, which consists of n different numbers. These are basically, as far as we're going to be concerned, these are going to be real numbers, but you could also think of a finite alphabet if you felt like it. At the output, you're going to have x hat. The alphabet x hat could actually be different from the alphabet x. It could be real numbers, but it could be something else. We're translating, using an encoder, those numbers, the n numbers, into some number of bits. And then on the decoder end, we're taking those bits and we're mapping them back to the reproduction alphabet. And ideally, of course, we would like it to be identical. That's not always the case. Now, one problem is, what if we don't know the source model? Ideally, we would like to know the statistics. We would like to know how X behaves, but that might not be the case in practice. Some additional problems that we encounter are, can we still have reasonable performance without knowing the source model? Will the performance go down significantly? And actually, it can be proved for both lossless and lossy compression that at least asymptotically, you don't need to know the source statistics in order to perform just as well as if you knew the statistics. And I'm emphasizing the word asymptotically. And this type of observation, that you don't really need to know the source statistics and still you can perform well, you can compress the data very well, that's what motivates the entire field of universal data compression, where the word universal here, its meaning is that no matter what statistics we have within the universe of possible statistics, we can still compress well. Now, in the lossless compression world, there's been a lot of work and a lot of very nice advances in universal compression. This is, for example, the work of Lempel and Ziv in the late 70s, another algorithm with Welch in the 80s. There's work by Rissanen all through the 80s and 90s. Context reweighting was quite a significant advance in the mid-90s. The bottom line is that lossless compression, even if you don't know the statistics, has been really mature for a while, since the early 90s. Now, in contrast, for lossy compression, where we're allowing some distortion between the input and the output, to put it pretty bluntly, we don't know anything. I mean, we know very, very little. And there's been a lot of people that have been trying to work at approaches that are related to what I'm talking about today, but the bottom line is that there's no standard, there's nothing that works very well, the algorithms might be very slow, they might compress very poorly. We're not there yet. Okay, so what are we really trying to do? Rate distortion coding is a field where we have that input X, and we're trying to basically derive X hat, the approximate version, where we allow distortion between the input version xn and the output vector x hat n. And that distortion is basically the average over the per symbol distortions. So xi is going to be the ith number at the input, and practically speaking, xi hat will be the ith number at the output. D is going to be some measure which tells us how much distortion we have between the input and the output. Very simple example, you can think about absolute value between 17 and 19. Square error. You take the error between the number at the input and the number at the output, and you square it. Those are the type of distortion measures that are typically used. We summarize over all the n numbers, and we take the expected value. Now, in 2008, Jalali and my co-author, Tzachi Weissman, they came out with a very interesting algorithm for basically lossy compression of bit vectors. And here we're going well beyond bit vectors. First of all, we're talking about the input and output alphabet being real numbers. So this is compressing stuff like audio, video, images. These numbers that we're interested in compressing are real numbers. And secondly, we are emphasizing the square error distortion that I just mentioned, but all of our theoretical results can actually support other types of distortion measures. So this is a significant strengthening of their result from bit vectors to real numbers. Now, if you look at a trade-off between the rate, the number of bits that we're spending to describe a certain input, and the distortion that we achieve between the input and the output, it's very clear that there's a trade-off here. If we spend a lot of bits, we may be able to get a very small amount of distortion. On the other hand, if we don't have many bits to spend, there's going to be a lot of distortion. So this trade-off is very clear, and it appears here in this plot of distortion D as opposed to the rate r. And what's very interesting is that at each point of this plot, the curve has a certain slope. And this curve overall is going to have some convex type of look to it. And because if it's convex, if we optimize for the minimum of rate plus some constant times distortion, that minimum will actually hit us tangentially onto the rate distortion function. The rate distortion function, as I just implied, it really tells you what's the fundamental limitation of how well I could compress the source, taking into account this trade-off between the rate and the distortion. Now, let's actually start discussing what we actually do. And I'm obviously skipping a lot of math, and I'm trying to describe this as intuitively as possible. We start by looking at our sequence, our vector of length n, and I look at blocks of k plus 1 characters. What are characters? In our case, characters are real numbers, but we translate them into a finite number of levels. More on that later. So we have this output alphabet y. Y is no longer real numbers, but it's a finite number of characters. And we're looking at a set, a block of k plus 1 of these characters. And then for that possible block, we're now counting, given the previous k characters, the previous k or the context, how many times did the next character k plus 1, appear? And the reason why we're doing this in the lossless compression world, it's very well understood that we have a dependency, a statistical dependency between the past and the future. And this situation where we're looking at the previous k characters, and now we're asking what is the next one, this type of thing models the data very well for many types of data. So we're really interested in, intuitively, in the distribution of the characters that come after this, these k previous ones. And I have a mistake here. They didn't follow m, they followed the k previous characters. M is actually the vector of all the statistics that we are counting empirically in the data. So first of all, we're counting statistics. We're counting how many times everything happened. And secondly, we're computing basically the conditional empirical entropy. The conditional empirical entropy is the coding length that I will need to spend in order to describe the k plus 1 character in the block, conditioned on knowing the k previous characters. And basically, all I'm trying to say here is that we're trying to calculate, we took our real numbers, we mapped them into a finite alphabet, and for this finite alphabet, we're trying to say, well, how much would it take to describe, in terms of bits, this finite alphabet? And soon this will become very clear, more clear anyhow. So once again, the number of bits that are required to encode all the characters that follow the k previous ones, and m is once again a mistake. All right. How would you proceed? So we have a technique that we want to translate real numbers into a finite set of characters. That finite set of characters, because it's finite, we can compress it without loss. However, there's a distortion from the input to the output because the input are real numbers and the output is over a finite set of numbers. So we're going to have distortion. And ideally, what we would like to do, we would say, well, what is our ideal x hat n? On the one hand, it takes into account the conditional empirical entropy, using that type of approach of, for every block, given the k previous characters, how many bits would we need to spend for the next character? And hk really means, given a model where this context, the past, is of depth k, how many bits in total do I need to spend for the entire y? Y is the output. Once again, the output is over a discrete finite alphabet. So a discrete finite number of real numbers. On the other hand, so I have this coding length, the bits, h. And that's one thing. That's the rate. And I also have the distortion. And the distortion is between x, the input, and y, which is once again over a finite number possible set of values. And the constant alpha basically represents a trade-off between rate and distortion. And as we saw previously, whenever we are optimal, we're going to be on the rate distortion curve. We're going to be tangential to it. Now, so ideally, this is what we would like to do. And if we could perform this computation of finding the global maximum, we could then describe the global maximum without loss using any universal lossless compression that we felt like using. And in particular, context-free weighting is a very advanced universal lossless algorithm. So we're looking for the global optimum, and then we're actually describing it losslessly. And there is going to be distortion. There's going to be distortion because the y's are going to be different from the x's. Once again, the y's are over a finite alphabet, although the x's are any real number. And here we have a theorem that basically, asymptotically, as n goes to infinity, the length of this vector goes to infinity, asymptotically, the technique that I just described will approach the fundamental limitation of information theory, the fundamental trade-off between the rate and the distortion. So this sounds very nice, but this has ridiculous complexity because we need to find the global optimum. And this search for a global optimum would have combinatorial complexity. So this is just not going to happen. We want to start approaching this problem in a manner that is more computationally tractable. To do so, for each sequence y, for each sequence y of length n, and once again this is over a finite alphabet, we're going to be assigning an energy function. The energy function will account for the trade-off between the number of bits, h, and the distortion, d. Now, with this energy function, we can start utilizing tools from statistical mechanics, and we define a Boltzmann distribution over the space of all possible outputs. And this Boltzmann distribution has the nice flavor that we're really trying to tend toward something that has the smallest energy possible. And there's an entire literature that talks about, in the statistical mechanical world, if you just let things happen, they tend to gravitate toward the lower energy solutions. And simulated annealing is an approach that it kind of begins with a very high temperature. A very high temperature in statistical mechanics means everything has the same probability. And very, very slowly, we're reducing the temperature. And as we reduce the temperature, things become more orderly. Things become less random, and we are attracted to the lower energy solutions. Now, the thing is, we can't just immediately take the temperature down very quick. The reason why we cannot reduce the temperature quickly is if we did that, we would, so to speak, be cooling something before it settled into nice crystal patterns. We want to get those nice crystal patterns. And in order to get them, we need to cool the system very, very slowly. Now, going from the analogy of crystals in statistical mechanics to the other analogy of compression, what we aim to do here, we're looking for something that is near the minimum. Maybe we're not going to get the exact global minimum, but we want something good. And if we reduce the temperature too aggressively, we're going to miss it. So we need to reduce the temperature gradually, just gradually enough. And as long as we can do that, we have an algorithm called a heat bath algorithm, which is, once again, in the analogy to statistical mechanics, we have a big container full of hot water, and in that container, things are eventually going to be converging over time to some distribution. And if we begin with hot water, that distribution is very random. And if we gradually cool it, the distribution starts being peaked toward the areas of minimal energy, which we are interested in. So the MCMC algorithm is a Markov chain Monte Carlo approach, which actually implements this in a simulation type of environment. It's an optimization algorithm where I have basically relationships. I have this energy, and I gradually modify my output. I work directly on my output, and I make random changes on my output where the probabilities are related to the temperature. And as I'm taking the temperature down, gradually over time, I'm going to be in a region where I have very low energies. And within that region, I'm going to be attracted toward the global minimum. On the other hand, I want to emphasize that this is random. So this is kind of like a heat bath. Anything can happen within the mechanical statistics. So what I really have is that at every point of time, concretely speaking, I'm choosing one of the n locations. This is one of the n characters at the output. And for that specific location, I'm going to be calculating a distribution for character number I conditioned on the k previous characters. And actually, there's a dependence, a statistical dependence, not only on the k previous characters, but on everything else. So conditioned on everything else, which is basically n characters taking out the ith character, conditioned on everything else, which is now constrained and fixed, I'm allowing myself to modify the ith location, and I'm going to be generating it randomly. And then what happens is that over time, by reducing the temperature, we're going to be, as j goes to infinity, the number of iterations, we're going to be tending toward the distribution of interest to us. Now, another thing is that, well, I'm not really going to describe this, but this is the distribution, the conditional distribution for the ith character, fairly complicated. But the bottom line is that this thing, although it looks very complicated, the computation for each individual character, each individual location, I, can be done in a very small amount of computation. When I'm saying small amount, to put things in perspective, my implementation in MATLAB, it does, I think, 50,000 of these per second. And as we all know, MATLAB is not very fast. So if we would implement it in a faster environment, these would be millions and millions per second. This is truly a reasonable algorithm in terms of computation. And here's the bottom line. Here's the algorithm. The algorithm basically loops over a large number of iterations from 1 up to r. Each of the times, it selects the temperature according to some formula. After selecting the temperature, it randomly chooses one of the n locations. It computes the conditional probabilities for that location, conditioned on everything else. So at present, nothing else will change, only that location number I will change. It updates that entire vector based on generating the ith location, and it needs to also update all kinds of data structures in order to go on to the next iteration. So that's the algorithm. Now, why does it work? What we're really doing here, we have an input and we have an output. And the output is a noisy version of the input. But it's not a random type of noise. It's a very specific type of noise. We're adding noise, which is basically distortion, in a way that makes the output very, very compressible. So you could think that I have a space. Actually, maybe let me now shift to the computer. Can you shift me to the computer? Okay. Let's see. How do I once again use the button up at the top, the arrow button? Oh, the one at the top. Okay. So yeah, I'm writing. Okay. So we have this space, and this is the space of possible outputs, and this is my input xn, and these are all the possible outputs yn. And within that space, this is a subspace of nearby outputs. So these are the locations that the distortion, okay, what did I do wrong? Okay, the distortion, clear. Okay, I'll do that quickly again. This is xn. We're mapping to the spaces of yns. And within this subset, the distortion between xn and yn is low enough. And within this set, I'm looking for the outputs that are very, very, very compressible. So this location will also be compressible. And it could be that this band is very compressible, and within that band, I'm trying to see where's the intersection between the compressible set and the low distortion set. So that's the intuition of what's going on here. Could you please move me back to the laptop? Okay. So that's the intuition that we're adding a noise that is very structured relative to the input. And now we have another theorem that's similar to before. When things go to infinity, the input vector and the output vector become infinitely long, and the number of iterations r is also going to infinity. Everything here is perfect. So, we're getting the same theoretical performance as before. This is very encouraging, of course. And this is actually, in contrast to before, the computationally intractable global optimization. Here, it works on a computer. So you could say that this is great, but unfortunately, there's no bound on the required number of iterations. And not only that, I kind of was not telling you that I was using an output alphabet which had been pre-computed in advance. And when I'm saying pre-computed, as n goes to infinity, I have an alphabet that grows very, 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 very gradually. And when n is small, the alphabet will not be big enough, and I'm going to have lots of distortion. And when n is big, the alphabet is big enough to allow moderate distortion, and then things will be fine. But with a large alphabet, the algorithm is slow. And we want to reduce the size of the alphabet. So challenge number one was a computational challenge of going from a global optimization to some algorithm, some optimization algorithm. Challenge number two, we can do even better using a small alphabet. Now, there's actually some hope here. There are results by Ken Rose from the early to mid-90s. Those results are actually not very well known in the source coding community. But what he showed is that when the Shannon lower bound is not tight, and the Shannon lower bound is something that you learn about in information theory. Ryan, is that true? Do you teach that?
Most of the time.
Okay. So when the Shannon lower bound, some condition in information theory is not tight, it so happens that the reproduction, the ideal reproduction alphabet is discrete. Discrete and finite and rather small in practice. Now maybe what happens when it is tight? You're failing your class?
What?
When the Shannon lower bound is tight, what happens then? What's the reproduction alphabet going to be?
Binary, I guess.
Binary if it's a binary problem, real if it's a Gaussian distribution at the input. So it could potentially be for the real numbered inputs that are interesting to us here, it could be a infinitely large alphabet. But my point here is that when it's not tight, this is no longer an infinitely sized alphabet. This is actually a small alphabet in practice. And because it's a small alphabet, we have hope to significantly reduce the complexity. And basically, the distribution of the input is unknown. And consequently, we know that there's a small alphabet, but we don't know what that alphabet is. So we encounter a new challenge. And the way how we address that challenge is that instead of having a fixed alphabet y, we now have basically an adaptive reproduction alphabet, where instead of optimizing Y, we're going to be optimizing Z. And Z is no longer a fixed alphabet. Z are like symbols, A, B, C, D, E. We do not know what numbers they correspond to, but each of them will correspond to a real number eventually. So we translate, we're optimizing over an alphabet of A, B, C, D, E's. Eventually they're going to be corresponding to numbers. And we optimize YI, which is the actual number, and it's a mapping from Z, the character, to a real number. And we're going to optimize over that. And this can all be performed efficiently. And here's basically the flow chart of the algorithm where we're emphasizing the new parts. So we generate a random location as before. We loop over all the possible characters. Right now the characters are not Y's, but they're Z's, A, B, C, D, E. And the new part is that we compute the optimal mapping from Z to the real numbers Y. And we do that at each iteration. It actually takes, there's a trick that it takes very, very little computation. That's actually the simplest part of the entire process. And similar to before, similar to the algorithm by Jalali and Weissman, we update the empirical entropy, the coding length. The only change here is really to compute the optimal mapping from the Z's to the Y's. That's the only thing that happened here. Now, once I've run this block, then I basically know the distribution for generating the current character. And I generate that, and I also need to maintain all kinds of statistics in order to calculate the mapping from the Z's to the Y's. Those statistics are not complicated to maintain. Once again, it's very fast. And that's the entire algorithm. Two modifications. We need to have data structures that support a mapping from Z to Y, and we need to compute at every single step. We need to update the mapping from Z to Y. So fortunately, it turns out that this has the same asymptotic properties as before, but using a much smaller alphabet. The results that I'm showing you here, which I'm soon going to go into in detail, these are based on alphabets of sizes 357. 357 is much smaller than 100, which the previous algorithm would have used. And of course, because I'm using a smaller alphabet, much reduced, greatly reduced amount of computation. Okay, so what are we seeing here? First of all, similar to before, the axes represent the rate and the distortion. The rate is the number of bits per input character. The distortion is the mean square error between the input and the output. And we're specifically discussing a Laplace source, which is IID, and every single Laplace number was generated independently of all of the others. Now, we're seeing several curves here. The bottommost curve, the red solid curve, is the rate distortion function. That's what hypothetically we could do if we knew everything in advance. And not only that, but the blocks would become infinitely long, and we had an infinite amount of computation, and everything would be at your disposal. And here, of course, I'm using n equals 50,000. So my inputs are of length 50,000. They're not going to infinity. The computation that I'm using is a constant number of computation per iteration. This lower bound is in a different world. Okay, so we're comparing a very fundamental theoretical lower bound to algorithms that actually work. Now, we also have another red line. And that red line is using an algorithm called entropy coding, which is quite commonly used, but it requires knowledge of the statistics. Once again, we don't know the statistics. We would like to perform well without knowing them. And here's two alternatives. One of them, the dashed dotted black line by Yang and Zhang, is an algorithm from the mid-90s. That algorithm is better than the entropy coding, but it actually trained on the statistics. So they take the input, they chop it into two, and they say, well, we're going to train on part number one. On part number two, we're going to actually run this thing. And they're saying that in practice, these are the results that they show with this training approach. And if they would have to, they have some trick how they can actually show the real performance, but then there would be a degradation. And the degradation would basically take them to the red line. Now we also have our results, the MCMC with the circles, and you can see that the circles beat the red line slightly. And recall that the red line, it knows the statistics. So you have the red line that knows the statistics. You have the result by Yang and Zhang, which the way how they show it, it trained on the statistics, which is kind of unfair. So they have an advantage. And our approach doesn't know the statistics whatsoever. And despite not knowing the statistics, it still beats the traditional approach, which is used in various applications such as JPEG, MPEG, and so on. Now, despite that, there's still much to do. But let's first summarize what we've done so far. We extended the MCMC-based approach from bit vectors to real numbers. And we've significantly reduced the amount of complexity per iteration by adapting this not very well-known result by Ken Rose that the output alphabet will be, in many cases, very small and finite, the optimal reproduction alphabet. And this is a result that, in our opinion, is not really appreciated, but it was very useful for us to give us confidence to work with small alphabets. Another thing is that we have promising initial results on synthetic data. But first of all, you can see that compared to Yang and Zhang from the previous plot, maybe we're comparable, but there's much to improve. And additionally, we're not really interested in synthetic data, but actually real data. So let me now illustrate, kind of illustrate. I see the shades of gray are not coming out too well. Results on real data. Now, these are, I took a wavelet transform on an image. A wavelet transform is when you take a large number of real numbers, you kind of do some linear algebra, and you transform them into a domain where most of the numbers are going to be very, very small. A small number of these new coefficients are going to be very large. So we've compacted the energy using an orthonormal transformation into a very small number of coefficients. That is basically, it compresses much better. Okay, what we have here at this corner, it's completely gray. This corner, I'm assuming that somebody compressed it for us. And based on the fact that we, so to speak, we're assuming that we have this site information available, from here, I compress these. So basically, there's a tree type of structure relating the wavelet coefficients going from this corner to this direction. Given the corner, I compress these three. Each of these, I compress them using the technique that I described, where the context, the k previous characters that I just described, takes into account these numbers, which are assumed to be given to us. And from these three, I get these three, which once again, they don't come out very well on the screen. Now, assuming that the corner was available, I'm basically compressing 15 out of each 16 coefficients, because this was 1 out of 16 of the area. And this is the number of bits that I'm requiring per pixel. Each number here, although it's a wavelet coefficient, it corresponds to pixels in an image. And this gives me a certain level of distortion, and this level of distortion is approximately comparable to image compression results in the literature. The good news is that it sounds comparable. The bad news is that somebody gave me this for free, the corner. And I need to somehow compress the corner. And the corner is actually the part of the wavelet coefficients which is most difficult to compress. So when I'm saying comparable results, that's not exactly true. There's a lot of work to do here. One direction for future work is algorithmic improvements. The specific type of compression algorithm that I was describing, the context tree weighting, we can do things that are much fancier. with some basically trying to understand the structure of the data and using more advanced algorithms. These algorithms would also possibly run slow, and some algorithmic work would be necessary in order to implement it very nicely. Another thing is, of course, we're gearing toward better compression in practice. I showed earlier that relative to Yang and Zhang, our results are not very good. There are several places where we believe that both algorithmically and from the information theory perspective, we can make significant improvements. And finally, this needs to be applied not only to images, but also primarily to video, because as I said at the beginning of the talk, that's where 80% of the data is actually located. So this concludes the talk, and I'll be happy to answer any questions.
Any questions?
Yes.
When you say it does not, you're using this universal encoder there, and I got the impression that your algorithm, because of its iterative nature, went through something of a training process. Is that true, not true, distortion? What's happening here?
The algorithm, if you think about the analogy to the heat bath world of statistical mechanics, the algorithm begins by guessing a possible output. Now, because at the beginning, at the high temperature, everything is completely random, from that initial point, it doesn't really matter what that initial point is. And we start gradually decreasing the temperature. And at a moderate temperature, there starts being a drift toward lower energy solutions. And then we decrease the energy further. Now, if we had reduced the temperature too much, what would have happened would be hitting some local minimum. We don't want to do that. We want to go toward the global minimum. Because of that, we want to reduce the temperature very slowly. Now, while we're reducing the temperature, we're taking into account the trade-off between, on the one hand, the universal compression algorithm, and one of the modifications for future work is to compute precisely the coding length. So use a strong algorithm, and at every point of time, based on the output that we have at that point of time, we want to know exactly what coding length it will take. Not an approximation, but an exact value. On the other hand, at every point of time, we know that the distortion from the input to the output. And gradually, because the energy function is accounting for the trade-off between the two, and we're kind of pulled toward lower energy functions, and as we reduce the temperature, although we're kind of, everything is random within the statistical mechanics world, we're gradually tending toward the lower energy solutions. So I hope that this kind of addressed your question.
Okay, well, let me re-ask it. You used a copy of the Lena picture there to say, okay, this isn't there. So, and you have a distortion on this.
Mm-hmm.
So, are you in essence tuning your coding algorithm for the Lena picture?
It will tune every time we will run it from scratch, and every time it will, just like the universal lossless algorithms, it will tune itself for the statistics of that specific image.
Okay, so if I traded off to the motorcycle starting gate picture there, the algorithm would not necessarily work on that image, and it'd have to be trained on that image.
Oh no, there's no training here in that sense.
You're tuning for the image, though. We're not tuning. We're starting the algorithm from scratch, and it knows nothing. So the results that you saw basically assumed nothing. If I would take a different image, it would learn the statistics of that image. The statistics of that image meaning the relationship between the different wavelet coefficients. The current wavelet coefficient that you're trying to compress, and the neighboring coefficients, and the coefficients that were basically in the corner. This is, there's no tuning involved here. The algorithm basically works from scratch.
Any other questions?
The heat bath algorithm that you described looked a lot like belief propagation or the sum product algorithm
It's closely connected, right?
You could use any optimization algorithm, essentially. So we have a highly nonlinear function, trade-off between the distortion and the rate. And for this highly nonlinear function, any type of optimization method might give better performance. Actually, initially we were not aware of the result by Yang and Zhang, and they have the exact same algorithm, but for a different optimization technique. And because of that, I mean, many of the concepts are very similar. It could be we believe that I actually corresponded with one of them, and he told me that it took them quite a while until they got the performance to work well. So we believe that tuning an optimization algorithm, not just following the rules blindly, will probably give much better performance, not to mention the improvements that I already discussed. Basically, using a better compression, a lossless compression algorithm, and accounting for the precise coding length that algorithm would require. But yeah, all of these different optimization techniques could be used potentially.
So, do things like exit charts play any role in the convergence results here?
I haven't really given this some thought, and this is probably something that we can discuss later. But yeah, I don't know.
Okay, finally, the convergence results I didn't catch whether those were for a subset of sources, like IID sources or ergodic sources.
That is for the very broad set of stationary ergodic sources. So just for the audience, I'll say that stationary ergodic sources essentially mean that if you're looking at the input over a very long amount of time, the statistics don't change. So that's a relatively very broad class of sources, much broader than IID, which means that each number was generated independently of the others. And for this broad class, we have the theoretical properties.
Okay, then one last question. And that is that then you must have the K in your algorithm growing.
Right.
The file length.
Right. So something that I kind of appeared in one of the slides, and I didn't mention, is that the K needs to grow as small O of log n. And once again, the computation is proportional to K, and as that small O of log n grows very, very slowly, but still grows, we have more computation per iteration. And similarly, as the alphabet size grows, the computation per iteration is linearly proportional to the alphabet size. That's what motivated us to reduce the alphabet size. Because initially, the initial algorithm would have required a much, much larger alphabet, and that would have been hopeless.
Any other questions? Yes.
So for any given real-world signal, so how important is the choice of the distortion measure?
The choice of distortion measure is actually very important because if, for example, if you're going to choose square distortion, but for the user, for let's say the human viewer, if that would be a very poor choice, it could be that you're optimizing for something which, in terms of the user, has very little functional importance. So that's actually a very good point. That square error is used by a lot of people because it's mathematically tractable. You can take derivatives. There are a lot of nice things, but it so happens that it corresponds visually when people look at different images. They seem to be okay with this measure, but other measures, which would be mathematically much more difficult, would still be better.
So how would the performance of that algorithm be affected by if the distortion measure is, for example, non-metric or some other complicated measure? It certainly have a significant effect on the optimization algorithm.
Right. If the distortion measure would be very complicated, then if basically you would need to calculate over the entire image, then this would mean that this calculation would take a long time, and this is per iteration, and that would be bad. Now, as long as you can calculate this with a small number of local calculations, then the distortion doesn't really change by much. So,
It's assuming that the measure is smooth again.
yeah, so implicitly, so the results that I indicated were specific for square error. The results can be easily extended to other types of, let's see, can we get the screen again? Okay, and how do I erase this thing?
Please go to eraser mode at the top, the button, eraser button.
The button. Okay, got it.
Hello, this is from
Okay, anyhow.
MCMC.
We're talking about when we have a distortion measure such as,
Can you hear me? Hello? Hello?
Maybe you can just give your answer verbally.
basically when we have this type of additive distortion metric, average over the n per location distortions, then everything is fine. Everything can be computed very easily. The moment that we have basically interactions between different locations, then things become complicated very quickly. And this is, of course, a somewhat flexible class of distortion measures, so it's not too bad. If you would have some small area of local interaction, that would also be computationally manageable. So that's actually less of an issue as long as the distortion measure is not extremely complicated.
I have a very quick question. In choosing your regime, your temperature regime, that's going to affect your convergence.
Right.
In fact, if you have, if your functional has a lot of, particularly if it's multimodal, and those modes are close to each other, you basically are very likely to jump over some of them and completely miss perhaps your
Right.
your desired minimum. So how do you choose it?
First of all, there are theoretical results. The theoretical results say that if the inverse.
In practice, I'm not saying.
Oh, you're saying in practice.
Yeah.
My personal experience is that this is a mess. I've spoken with a person who is quite an expert on optimization, and he told me that the world of optimization is dominated by ad hoc algorithms. So you can prove something, but it might not work very well in practice. And he suggested that I try all kinds of ad hoc approaches, and that there are not going to be any proofs. These approaches will, of course, be motivated by this type of, rigorous optimization approach. But he was saying, look, I mean, you're going to get much better performance in practice if you use ad hoc.
Excuse me, is North Carolina ET?
All right. Yes.
Yes, okay. We have a couple questions.
Yes, please.
Sure. One question is in the beginning. Also, you repeat basically the loss. You can data have loss because people have different perspectives. So how you counting the model for the people's activity algorithm?
Wait, okay, so because I was far from this, can you understand?
No, because they just upped the volume. I didn't hear
Oh, I
anything.
see. Could you please repeat the question?
Could you please repeat the question?
Okay. The question is, the lossy compression, depending on people's perception, didn't capture all the. So, how your lossy compression algorithm accounting for this model. How do you know your lossy compression is consistent with both perspectives?
Okay, if I understand, you're asking whether how I know that the compression is consistent with the model that the data actually belongs to. Is that correct?
Yes.
Okay, so that's the reason why we're highly interested in universal algorithms. That regardless of the model, within the universe of all possible models, they are asymptotically going to converge to the best possible performance for that model. So we're not here, as I was answering Joel's question earlier, we don't know anything about the specific model. We have an algorithm that basically will adapt to the specific model. Did they hear me, or?
Yeah, I think they heard you. Any other questions?
Yeah, another question is when you have this lossy, you say you're you're doing for the pictures, you say you can expand to videos.
Mm-hmm.
Right now, all the video stream using some compression. So
Right.
how your algorithm is compared to them?
Right. So the way how we envision this is that right now the video, it goes through a lot of different transformations. There are a lot of steps in the compression. And one of the steps is to use entropy coding, which I illustrated in a simulation graph. And we believe that instead of using entropy coding, you could use a technique such as we're suggesting at that level in the hierarchy of all the compression steps that are being performed. And we hope that you would be able to basically outcompress the entropy coding for that block within the video coding setting. We're not thinking in terms of taking a huge bunch of 100 billion pixels and running the algorithm on 100 billion pixels. That would be very, very difficult. We're talking in terms of let's isolate the block within the video coding where the entropy coding is currently working, and once we've isolated that block, let's replace it by this new technique.
Okay. Then both compression can be lossy, right? So your target is reduce some of the volume. But if you reduce some data, then you have better compression. Then you try to get the same kind of region for people. Is that kind of target? So how to compare the end result? Let's say you reduce the data by 20%, but if people say the quality is worse, or how that can be compared?
When you're talking about quality, you mean the distortion or the coding length?
The quality for the videos.
Yeah, so what taking into account that we're performing a trade-off between the coding length and the distortion, we hope, and of course, this will require improvements, the current practical improvements of the current algorithm. We hope that it will be possible to reduce the coding length by at least eventually by 10-15%. The reason why we have that hope is we know what the gap is between entropy coding and the rate distortion function for a variety of different statistical sources. And we're specifically talking about statistical sources that video wavelet coefficients have been seen to be well matched to those sources. So there's 10 to 15% in terms of bits. It could be done. If we get 6, 7, that would be very nice. We're definitely not there yet. This requires further work, but we might get there.
Yeah, that's basically the reason I asked you in the first question about the perspective model, because when you have wholesale result and the lossy, lossless people can compare easily. Lossy data is hard because you don't know which one have good quality or not. So that's the kind of same question. Okay.
Yeah, so that's, basically because because we don't really, we don't really know what the model is, and because of that, that's why we're using the universal compression. But again, based on simple models, at least, that have been empirically observed to be reasonable, we think that there's some room for improvement. That's where we're hoping to go in the future world.
I have one quick question. Yeah. Okay. How is your approach compared with the existing JPEG 2000 using the wavelength coefficient for compression? Is that comparable to yours and the current, the JPEG 2000 standard?
Comparable in terms of performance, or comparable in terms of how it works?
Your approach seems very different. You derive from the lossless approach, where most of the JPEG 2000 they go directly from the source coding. It's a very different approach. So can we comparison?
Well, yeah.
With the existing the standards.
Yeah, that's a good question. Compared to the JPEG 2000 image compression standard, and I'll just tell the audience here that it is based on, similar to what I showed on, wavelet transformations. Compared to that standard, what we're doing, we're taking entire subbands of wavelet coefficients and we're running our algorithm on them. This is radically different from what's done in JPEG 2000. We hope that with some more work, we can provide a nice savings in terms of the number of bits. Because once again, JPEG 2000, there are several levels in terms of what's being done there, but it's relying on entropy coding. Entropy coding is not really very close to the rate distortion function. So we hope that we can make improvements there.
Okay. Thank you. We will use PSNR. PSNR versus the for those different source coding, the lossy compression. But in your case, you're using the rate distortion function. So it's slightly different from the most table comparison. We're using the PSNR between the original and the reconstructed image for given rate. So that's most time the compression algorithm compared. So that's the thought.
Again, I think that there's room for improvement. This requires more work of an applied nature, and until we carry this out, it's too early to say. So Hamid.
All right. Well, thank you very much. Thank you. Let's thank our speaker.
Thank you.
Thank you.